Hello friends and welcome to your channel GATEquestionsECE. So I am back with next question in this series of random variables and the question code is 118. Consider two independent random variables x1 and x2 such that x1 is uniformly distributed over interval 2 to 5 and x2 is uniformly distributed over interval -1 to 1. If z is maximum among these two random variables x1 and x2, then find the PDF and CDF of z probability that maximum of x1 x2 is less than 2 expectation of z and variance of z. So let's see how to solve this question. So let's write first what is given in this question. So it is given that x1 is uniformly distributed over interval 2 to 5 and x2 is uniformly distributed over interval -1 to 1. Also it is given x1 and x2 both are independent of each other. So it is a case of independent random variable. And it is given z is equal to maximum among x1 and x2. So from our previous discussions in previous questions, we have seen that for two independent random variables, the CDF of z for sample value small z is equal to the product of marginal CDFs of each random variable x1 and x2 for sample value z. So differentiating both sides with respect to z, we can get the PDF of z will be equal to, so writing first term as it is times the differentiation of second term, and differentiation of this CDF will be its PDF of x2 z plus differentiation of first CDF, so that will be the PDF of x1 times the CDF of x2. So we will be using these two expressions to calculate the CDF and PDF of z. You can observe here that to calculate the PDF and CDF of z, we need to write down the expressions for the CDF and PDFs of x1 and x2. So let's first write down the PDF and CDF expressions for x1 and x2. So it is given that x1 is uniformly distributed over interval 2 to 5. So we can write that the PDF of x1 for sample value small z will be equal to 1 by 5 minus 2, which will be 3, for range z greater than 2 and less than 5, and it will be 0 otherwise. So the CDF of x1 will be equal to the integration of this function. So integrating, we will get the CDF of z will be 1 by 3 z minus 2 for interval z greater than equal to 2 less than equal to 5, and for z greater than equal to 5 it will be 1 and 0 otherwise. See, you can easily calculate this integration by drawing the PDF of x1. So if you draw the PDF of x1, you can see it is uniformly distributed over interval 2 to 5 and its height is 1 by 3. So integration of this will be, this is a constant value, so integration of this will be a straight line with slope 1 by 3. So you simply draw a straight line here with slope 1 by 3, and now you can write down the mathematical expression and you will find out that it will be this expression, and above this value for z greater than equal to 5 it will be always 1. So this is the CDF of x1. Similarly, we can write the PDF of x2. So the PDF of x2 will be 1 by 1 minus minus 1, so that will be 2, for z lying in range -1 to 1 and 0 otherwise. So integrating this, you can again draw the PDF here. So it will vary from -1 to 1 and it will be uniformly distributed over range -1 to 1 with height 1 by 2, and its integration again will be the same diagram that we draw earlier. So above 1 its value will be 1, and from -1 to 1 it will be a straight line with slope 1 by 2. So now you can write the mathematical expression for the CDF of x2. CDF of x2 will be, for sample value small z, will be equal to 1 by 2 z minus 1. So that will be z plus 1 in range z greater than equal to -1 less than equal to 1, and it will be equal to 1 for z greater than equal to 1 and 0 otherwise. So now putting these expressions of PDF and CDFs of x1 and x2 in these two equations, we can easily get the CDF and PDF of z. So the CDF of z will be product of these two CDFs. You can calculate the product diagrammatically here. You can observe here that this CDF is 0 for all the values below 2. So when 0 is multiplied with anything, the result will be 0. So we can write that fz will be equal to 0 for all the values z less than equal to 2. And you can note for this CDF, the value of CDF will be 1 when z is equal to 2. So above 2 it is always 1. So anything multiplied with 1 will be the same thing. So we can write that for z greater than equal to 2, the CDF expression will be same as that of this CDF, that is f of x1. And you can observe here that for z greater than equal to 2 and less than equal to 5, it is 1 by 3 z minus 2, and for z greater than equal to 5 its value is 1. So which is the same expression that we observed for the CDF of x1. So this is equal to f of x of 1 of z. So you can observe that the CDF of z is exactly equal to the CDF of x1. So let's try to understand why the CDF of z is coming out to be exactly equal to the CDF of x1. You can observe here that x1 belongs to range 2 to 5 and x2 belongs to range -1 to 1. You can observe for this interval that any value in this interval is going to be greater than any value in this interval. So we can write that the maximum among x2, x1 for this intervals will be always random variable x1, because this interval is always greater than this interval. And also you can note here that these intervals are non-overlapping. Any value lying in this interval does not lie in this interval. So this is the reason z is coming out to be exactly equal to x1. So not only the CDF of z is coming out to be exactly equal to the CDF of x1, its PDF also will be exactly equal to the PDF of x1. So you can differentiate both sides with respect to z, and immediately you can conclude that the CDF of z will be equal to differentiation of this will be PDF of x1. So we can conclude here that if the intervals are non-overlapping and random variables are independent, then maximum will be equal to the random variable for which the interval is maximum. This is not only true for the uniform case, it is true for any kind of PDF. I will explain this on next page. Suppose you have a random variable x1 that belongs to interval a to b, and random variable x2 that belongs to interval c to d, and intervals are such that a is smaller than b, and b is smaller than c, and c is smaller than d, and the PDF of x1 is f of x1 for sample value small z, and the PDF of x2 is f of x2 for sample value small z. Then we can always write that the maximum of x1 comma x2 will be always equal to x2, because here interval c to d is going to be always greater than interval a to b. So we can conclude that for independent random variables x1 and x2, such that such that x1 belongs to interval i1 and x2 belongs to interval i2, and i1 and i2 are non-overlapping. So if these two conditions, one is they should be independent and other is non-overlapping intervals. So if these two conditions are satisfied, then we can write that random variable z, which is equal to maximum among x1 comma x2, will be equal to one of these random variable, say xi, where I corresponds to maximum interval random variable. Random variable. So if interval I1 is greater than interval I2, then we can write z will be equal to x1. And if the PDFs are such that interval I2 is greater than interval I1, then we can write that z, which is maximum among x1 comma x2, will be equal to x2. For example, if we have x1 which belongs to interval say -1 to 2, and x2 which belongs to interval 3 to 5, the PDFs are not known, then we can directly write that z is equal to maximum among x1 and x2, since these two random variables are independent and here these two intervals are non-overlapping in nature, so this will be equal to x2. Also, this is not true only for two random variables. Even if we have n random variables, that is z is equal to maximum among x1, x2, x3, comma up to xn, where all these random variables are independent and intervals corresponding to each are these intervals, and they are also non-overlapping in nature, then we can write that z will be equal to one of these random variable which has maximum interval, that is interval which is greater than all of other intervals. So that random variable say xi. Also observe that one other case is possible in which all these intervals may be overlapping or few of these intervals may be overlapping. Then this result is not valid. That case we will see in the next question that I will bring to you. So now let's return to our question. So we have solved here part A. Now let's proceed to part B. So in the part B, they have asked about the probability that maximum x1 comma x2 is less than 2, or we can write z is less than 2. So this probability will be equal to the CDF of z calculated at sample value z is equal to 2. So that we can obtain by putting z is equal to 2 in the expression of CDF. So putting here z is equal to 2, we will get 0. So this probability is 0. So now we will see part C. So the expectation of z for this will be equal to expectation of, since z is equal to x1, so we can write expectation of x1, and since x1 is uniformly distributed over 2 to 5, so its expectation will be the midpoint of 2 and 5. So the answer will be 5 plus 2 by 2. So that will give us 7 by 2, which is equal to 3.5. And last, variance of z. So this will be equal to the variance of x1, because in our question z is equal to x1 for given PDFs. So this will be equal to the variance of uniform distribution is del square by 12. So this will be equal to, so this del is for random variable x1. For x1 del is 3. So 3 square by 12. So that will give us 9 by 12, which will be 3 by 4. So the answer is 0.75. So in this way you can solve any question that appears in the GATE exam or even in any other exam. So I hope you are liking my videos, and if you like this video solution, then please do press that like button below this video and subscribe to my channel for more such videos in future also. So in the end, thank you all for watching this video solution.